Hello, my name is Darren White, and the purpose of this video is to give you an idea about how you might go about introducing lines and angles to Key Stage 3, maybe in Year 7. This is not intended to be some pick up and use lessons. This is some ideas about how you might question, introduce activities. The important thing is to focus on if you're going to get some good, deep understanding amongst your students. Okay, so where do we begin? Well, as usual, we begin any module by thinking exactly about what previous experiences they're likely to have had in this topic and any misconception they're likely to have created. Then we want to be very clear about where precisely our unit is going and why that is our destination. And then we want to think about what precise understanding we want the students to have at the end of the unit and the potential pitfalls that might arise so that we can hopefully swerve them and avoid any further misconceptions. Okay, so at Key Stage 3 we can see that the students have measured angles before and they've come across various things about angles in a straight line and vertical opposite and missing angles. Okay, they've also been working on triangles and quadrilaterals. Okay, so we're going to try and make sure that we address any misconceptions that are developed here, but also to build on this knowledge so the students aren't feeling like they're just being retaught something that they've learned before. You'll see here that also I put in some Key Stage 3 objectives for algebra. The reason for this is that geometry is a perfect vehicle for bringing in some of the algebra in a kind of applied way, so that the students can build their algebra skills alongside their geometry skills, looking at expressions, equations, variables, etc. Really getting a good grip of why we would use them and some more opportunity to practice that area of maths that they've just been learning about. You can see the Key Stage 3 program of study on angles is quite dense. There's a lot of it. We're not going to be able to do all of that in one hit. So therefore, the focus of this unit is more going to be around how we draw, measure angles in geometric figures, some constructions, talking about these kind of notation and conventions for labeling, etc. And also we're going to be looking at properties and also these ideas of angles at a point, straight line and vertical opposite angles. And we're going to apply those rather than just teach them because, as I mentioned, they've seen that before at Key Stage 2. Okay, so where exactly are we going in this unit? Well, here I've got the skills that we're going to be addressing. I want to really highlight this idea of mathematical literacy. So geometry is a very sort of quite dense, complex topic. And when we're talking about mathematical literacy, we're not just talking about the immense number of words that they need to learn or conventions they need to learn. What I'm talking about is the abilities of the students to be able to describe their maths in a correct mathematical way. So getting up that confidence in being able to describe the angles and shapes that they are working with. So that's going to be really big in this unit. So beginning, I really need my students to understand the idea of an angle being a measure of turn rather than the distance between two lines. So I might show them in a video like this. The link for where I've made this video is in the supporting documents, where I'm really trying to emphasize this idea that the lines are one line is turning away from the other line around the center, which is where they normally traditionally considered the angle to be. So the idea that the quarter turn is 90 degrees, half turn is 180 degrees. When they get all the way around, they've got 360 degree turn. So that if I'm talking about an angle such as, say, 78 degrees, then I'm not looking at the distance between the lines, rather I'm looking at the amount of turn between the lines. It's really important that students get that concept really sorted right at the start of this unit. So we might go on to look at a diagram such as this, where we might say, I'm stood facing A, I turn to face F. How many degrees have I turned through? Maybe I might ask the student, if I'm facing A and I turn to face D, how many degrees have I turned through, and then ask the students to then create some sentences themselves where they're actually using the sentence, how many degrees have I turned, within what they're saying, so that they get confidence in saying that an angle is a measure of turn. Diagrams such as this will help this. This might be a pair share activity where the students are actually generating a description of what they know in each of these diagrams, bringing in some of that polygon knowledge that they've got from Key Stage 2, and start to describe these angles in respect of the amount of turn. And then we might finish off with a box fill exercise such as this, where I might say, starting at 0 and going round clockwise, count how many degrees would go in each of the boxes. And once they've got this idea of turn really sorted, we can start to think about how a protractor works, because protractors are famously difficult for students to use accurately. But once they get the idea that they are turning from a point, so therefore the center of the protractor needs to be on the point between the two lines, where the two lines meet, if you like, making sure that the 0 is on the line, and then it's no longer a guessing game which scale they're going to use. They're moving around from 0 and turning around from 0. So on this one, they can see that they're going to use the inner scale rather than the outer scale. Okay, we might then try putting the 0 on the other line and seeing when we would use the outer scale. Okay, don't forget to use different views of our angles. Okay, it's so easy just to give angles that are all the same way up, rotate it round. The skills are the same, the discussion is the same. It's just a different experience for the students. Okay, again, in our school, we like to use 360 protractors, full term protractors, as well as half term protractors, just to give that different experience. Okay, but the ideas are the same. How are you placing that protractor on? How do you know that this is an angle of 50 degrees or 310 degrees? Get the students to actually explain how they know it is. Yeah. Get the students to be able to describe where the way in which the protractor has been placed in order to read this angle. Once the students have got that sorted out, we can start to look at common misconceptions, such as this one. If they start off by giving the angle without the protractor on, get the students to estimate its size. They will then know when they see this picture that it can't be 310 or 50 degrees. It must be something else. Then they can start to explain what mistake has been made in the placing of this protractor. Okay, so measuring a reflex angle. If I'm going to give it a full-term protractor, it would be a different skill to if I give a half-term protractor. With a half-term protractor, I need to measure the acute angle and take away from 360 degrees. And by doing this, we are starting to introduce this idea of angles in a full turn being 360 degrees and how we might use that. Where's the turn here? Okay, well, I'm going to give this as a question to the students, and they might first be very confused by the question. What am I saying? What I'm actually going to do is I'm going to ask the students to build their understanding of the letter notation for geometry without actually telling them how it works. If I ask a question, where's the turn here, they automatically have to start using the letters to describe the turn, and they'll be able to generate that their understanding of their notation without me instructing them on it. So they'll start to talk about the line DE and the line EC and the angle CED, and they'll be unsure about it and uncomfortable about it, but it will help them with their understanding as we go on. And then when we talk about this one, surely the angle PQR would be this one on the inside. I want the reflex angle, so the students need to get more precise about the way they're describing. So if I go back again, we're talking about the acute angle DEC on this one and the reflex angle PQR on this one. So the students are really getting to understand that each angle actually contains two angles, a reflex and in this case an obtuse angle. Okay, bringing in this misconception here, the angle shown is ABC. Is it really? The students need to now be quite comfortable about talking the fact that this is either angle BAC or CAB. Okay, I'm going to start to introduce this hat symbol next to make sure that they know that they're talking about an angle. And the reason I'm doing that is because shortly we're going to be talking about triangle ABC. So on this one, okay, we're going to talk about the angle CAB and that hat symbol going in there to say the angle CAB. And actually, do we not want to say the acute angle at CAB? Okay, following on from that, I'll be able to then give an image such as this and ask the students to describe things on this. If I ask you about angle AED, can you see another angle that's the same as AED? So the students will then be looking. They're actually going to say, what about another one and another one? How many different angles in this shape are the same as AED? Okay, and then I can ask them about the angle ADB. What do they know about that? And how about the triangle ADB? And can you tell me two triangles that are the same as BDC? Can you give me a triangle that's the same? Is there another one in there? Could I put in another line to create another one that's the same as that? So then we can then start to get some good understanding of how the letter notation is going to work. I might give them an image such as this, get them to highlight certain angles. Highlight for me the acute angle at EID. And then we might make a key going down the side here, okay, with the way they're highlighted colour and the angle described using the letter notation. Just building up now, I might be able to now talk about a line parallel to PU. And by doing this, we need to talk about what we mean by parallel. I might talk about perpendicular lines, and therefore I might say QPU. What do you know about that? Can you tell me another line that contains a 90-degree angle? Okay, so can we talk about lines that are perpendicular to each other? Can you tell me about the green triangle? What do you know about that green triangle? What letters would you use to describe it? What kind of triangle is it? Can you tell me anything about triangle, RST, etc.? You get the idea. Going back to this idea of parallel, students often come to us thinking that parallel lines never meet. Well, these two lines don't meet. Are they parallel? We need to really hone in on their definition, make sure that they've got it nicely sorted. How come these lines are parallel and these ones aren't? We could start talking about the perpendicular distance and just get a better definition sorted for the students so that going forwards they really understand what we mean by parallel lines. At the start of this unit, if I gave them this shape and said describe it, they would say most likely it's green, it's L-shaped. Now I'm asking them to describe the shape mathematically. I'm hoping that they'll be able to get quite a lot of description from such a simple question. We'll be able to see how far they've come in their understanding of geometry and also their confidence in their ability to describe their maths. Going on to construction, so quite often the way that this would be taught is a teacher might say, draw a line of 5 degrees and measure an angle of 60 degrees, etc. I'm not going to do that. I'm going to ask the students how they would draw this. Actually have a go at it, make a few mistakes, start to get a list of instructions in order to draw this. So they're going to have to start off by drawing perhaps the angle of 5 centimeters. They'll realize themselves that they can't draw the 3.2 centimeters until they've drawn the 60-degree angle. So they get a list of instructions that works for them. Does it matter that we don't know the length of A? Why not? So really getting to the students to understand themselves by having a go at themselves and making mistakes and getting it wrong and realizing they can't do things. That's all part of the learning process. I might then go on to give them 2 triangles like this and ask them what's different in the way that they construct these, so they can come up with a list of instructions for drawing each of these triangles and recognize the difference between them. So I'm not having to tell them about this being a side angle side and this being a side angle straight away. We can discuss that later. First, I want them to see the difference between the way we're going to treat those triangles. Just a quick word about constructing triangles. When we're doing this work, always get them to measure the angles sum them up, see how close they are to 180 degrees. They've learned, as we mentioned before, Key Stage 2, about the fact that triangles sum to 180 degrees. We're going to use that to check their accuracy of their measuring and also reinforce that rule. So we're not reteaching that rule again, we're just using it in checking the accuracy of our measurements. Okay, I'm now going to move on to looking at angles in a full turn summing to 360 degrees. They've seen this before. I don't want to tell them that they should sum to 360. I'm going to give them this image and let the students describe what's going on here, get them to realize that this must be a mistake here somewhere. And if you've got high attending students in there, they're likely to be able to point to where the mistake is. This is sum to 90 degrees, but clearly bigger than a right angle. It's quite a nice activity without me having to tell the students about the angles in a full turn summing to 360 degrees, and that's what they're looking for. Okay, so just talking about building on Key Stage 2 understanding. These two questions here are pretty much like they'd see at Key Stage 2. They would be told the angles in a straight line, sum to 180 degrees. I'm going to avoid that language. I want to talk about the angles in a half turn, summing to 180 degrees. But the principle is they're going to find out what number would be added to 153 to make 180 degrees. But when we're building on that, moving that knowledge forward, I want to talk about the relationship between these variables. And this is where we can really start to use the algebra that we've seen recently in our Year 7 modules. These two variables are related to each other. They're related to each other because as this one gets bigger, this one gets smaller, and they add up to 180 degrees. And really sort of going to town in the understanding of that idea. And we're also going to make sure that we have this literacy coming in here. Okay, don't avoid this complicated looking stuff of angle E in terms of angle F. I want the students to be working with that straight away. So I'm going to expose them to this. Okay, they've got plenty of time to fully understand how to use this language. That's what I'm looking for. I'm looking for them to be exposed to it and be familiar with this kind of language. So they're going to say here, E equals 180 take away F. Okay, that is angle E in terms of angle F. Okay, going back again to these are kind of Key Stage 2 kind of examples. Okay, we're talking about bringing the idea that this is a variable. Yeah, as we change this angle, it's going to change the size of X. Change the size of X, it's going to change the angle that's in here. Okay, and then just cranking it up a little bit so that it's a little bit more complex. Here we've got 2x at 130 equals 180. So we're sort of making sure the students are seeing this as an equation to solve, so that when we go on making it even more complex here, and now we've got we've got 3 terms added together to equal 180 degrees, and making them realize that writing the equation is helpful. When I give this to students, often they'll tell me that this is 30 degrees, and I ask them why, and they say because their primary teacher taught them it. Okay, but I want them to convince me. I want them to actually convince me why this is 30 degrees, so they can work out this angle, because the angle in a half turn equals 180, and then they can then go on to work out this angle, because these two angles sum to 180 degrees, and then they can see that these two must be equal to each other, so they get an idea. They're able to convince me that vertically opposite angles are always equal. Or are they always equal? Here's how my vertically opposite angles are equal. Here's some that look vertically opposite. These not equal. So we can really start to sort of hone the idea of what we mean by vertically opposite and what is not vertically opposite. And it's really important that we go through this conversation with the students to try and put to bed some of those misconceptions. So look, I'll put this in as saying developing the explanation, not just angles of opposite each other. We need to make sure that we're talking about angles formed by crossing straight lines and vertically opposite are equal. Okay, so just sort of working up now our equations making them slightly more complex. This is a really nice one because we get an unknown but on both sides, which can seem a bit abstract when they're doing it at so a little bit earlier in the algebra unit, but we can see here why you'd end up with an equation with an unknown but on both sides, and they can actually apply that knowledge here. I put this one in because different attainment students would come up with different ways of doing this. Some would see this as 13q add 10 equals 270. Others would write 8q plus 4 add 5q plus 6 add 90 equals 360. So just giving them an opportunity to see different ways of doing it. Okay, we're neither of them are right or wrong. We've just got slightly more precise ways of doing it. Okay, what do you know about this triangle? I'm trying to come up with the idea here that we've got the same variable in each of these angles, so therefore they might be able to recognize that this is an isosceles triangle. Once they've worked out the x, they've written their equation and worked out the value of x, they'll see that they're the same size. Okay, we can talk about the features of an isosceles triangle as we go along here. Actually getting them to realize the importance of looking at these variables and also setting up the equation to solve it. Quick note about geoboards. We do these kind of pin boards and elastic bands a lot in our faculty. The reason for this is it gets the kids to really get hands-on with their work. I might give them one of these and ask them to make as many different triangles as they can and start to describe them. The students are straight away being creative, and then we might come back and we sort of like all make the same one, and now we're going to describe in more detail, make sure that they've got some good understanding about how you would describe this and how they could convince me that this is in fact an equilateral triangle. Once we've done a lot of work on this, I might then ask them to pinch the middle of one of their sides and lift it and place it over the middle pin, and now we've got an entirely new shape, and I can ask what's the same and what's different here. Okay, they might see that this angle here is still 60 degrees. We see these lines haven't changed their length, but suddenly we've not got a triangle, we've got a quadrilateral. Some of the students might know what this quadrilateral is called. We can start to justify, convince me that these angles have been halved and are actually 30 degrees. So it's slightly tricky to convince me of that. Okay, therefore these lines are the same length, and now we can start to talk about how big this angle is here. Sometimes it's good to put an elastic band down the middle here to help students do this, made up of two triangles. So there's a lot of maths that can be got from working with these pin boards. Standard and non-standard views. Okay, if you Google isosceles triangle, you get thousands, if not millions, of images all this way on. Okay, and very few that have been tilted and shown in different views. And the problem with that is that the students start to talk about the base angles of an isosceles triangle, but then they can't identify where the base is unless it's in a standard view. So we've got to make sure that we give the students lots of opportunity to look at various shapes and anything we do really in a non-standard view, so that they can get better understanding of how they work. One way we might use the standard view and the non-standard view is to just make a triangle on a pin board and then rotate it around. And then once we rotate around, the students will be completely happy that the lines are the same length, the angles are the same angle. It's just they're looking at a different view. And it's just a really nice way of saying that. If you don't have pin boards in your faculty, then you can get paper copies of them, big sheets of them, from the NVICH website, which you can get the students to draw the triangles. It's still a very valuable activity. Okay, just going to finish off by talking about this idea of using compasses to locate a point. I love doing this with my students. When you give them their compasses and ask them what they're for, they will tell you they're for drawing circles. And we need to address that and say, actually, they're for locating positions on your paper. Okay, and we're going to do it in this way. I'm going to give them a line which is AB, and then I'm going to say that C is exactly 5 centimeters away from A. Where could that C be? We could get the students to start to describe where precisely C is B, they'll start to understand that it curves around here somewhere, and then we can then draw it in like this, and we know we've got a circle with radius 5 centimeters and the center at A. We can start then to think about C is somewhere around this line, this orange line here, and then we can then talk about, well, what if we give another condition? Now I'm going to tell you that C is 7 centimeters away from B. Where might it be now? So they start to understand that they need to put their compass point on B with a radius of 7 centimeters and draw a new curve. And then we know that the point C is somewhere on this orange curve and also somewhere on this yellow curve, and so they will start to recognize where in fact that C might actually be. And then if I talk about the triangle ABC, it must be there, or maybe it might be there. Once they've got that good understanding of how their compass is going to help them locate the point, then we can start giving them further questions to do, such as this one, which of course 6, 8, 10 is an enlargement of the 3, 4, 5 triangle, so that's going to give them a right angle triangle for them to notice. And now we can start to introduce variables to our triangles. So here I can see I've got a triangle that's got size 5, n. What do we know about this triangle? So we've got a repeated letter here as our variable. What do we know about this triangle? Then we can start to draw them. What about if n is 6 or n is 8? And then students can then start to see what's going on here, start to make observations about it, such as what happens if the base angles, if the n gets greater, so as it gets taller, what happens to the base angles? Then we can go back and say, what if n is 5? Is it still an isosceles triangle? And then we're in a position to then make a prediction without drawing it. Can you describe what this triangle would look like when n equals 20? This is too big to draw, but the students should be able to come up with quite a good description of what their triangle might look like. And now I'm going to think about non-triangles. So here I've got a 4, 5, 11. And then when the students try to construct this one, they'll go, oh no, something's gone wrong. This doesn't make a triangle. Why not? What is it about these numbers that will stops it from making a triangle? Can you find a different set of numbers that will also not make a triangle? What's the rule here? What's the smallest possible triangle, isosceles triangle with a base of 6 that can be made? And you can challenge them to try and make a really, really small isosceles triangle with a base of 6. See what they can come up with. So that's probably quite a lot for this unit of work, and we should be able to, by following some of these ideas, get some good deep thinking about the basic premise of angles into the students' minds. Okay, where we're going to go next? Well, in year 8 probably, or perhaps later in year 7, we can start to bring in some of these other rules, such as parallel lines, alternate and corresponding angles. Yeah, and also we've talked about some of the angles in a triangle summing to 180 degrees, but we want to be able to, the students to know how they would prove such a thing, and that would come up in the later unit. Anyway, I hope you found this video helpful, and I hope that you'll now can go away and plan some successful lessons on points, lines and angles. Goodbye.